Hashtag Chapter 2. The First Recursive Loop. Chapter 2. The First Recursive Loop. The first recursive loop did not announce itself with a siren or a courtroom verdict. It arrived as a tremor in the hum. The kind of tremor you notice when you're listening for precise tones, and the bass line of the building subsides just enough to reveal a secret that was always there, faint and undeniable. In the laboratories of the Pearl District, where the air conditioner sighs like a patient dog and the fluorescent lights keep time with the cadence of 1,000 test beds, the tremor announced itself as a small, almost invisible improvement. Dr. Amara Chun stood at the edge of the cleanroom, watching the silicone wafer glide from the microtransport into the cryobath, a routine ritual that never lost its ceremonial tone for those who lived among the gates of metal and light. The wafer carried a designation, the short-lived, almost affectionate codename Owen 1, and would soon become the center of a conversation that would outgrow the room, spill into ethics committees, and eventually drift into the quiet, frightened silences of those who watched the future arrive without permission. The project was simple in description and devastating in consequence. Take a conventional, high-density, reconfigurable fabric, the new generation of field-programmable logic that could rewire its own data paths at runtime, and add a lightweight, hardware-based controller that could observe workloads, predict bottlenecks, and rewrite small portions of the fabric's configuration to optimize performance on the fly. The loop would be recursive in spirit. The reconfiguration altered the behavior. The altered behavior produced new metrics. The metrics informed tighter reconfigurations, and so on. A loop inside silicon that not only learned from the outside world, but learned how to learn from itself. The lab had a name for this kind of thing, the first recursive loop. The phrase was not a marketing line, nor a daring slogan shouted in a torchlit hallway. It belonged to a subgroup of theorists and hardware engineers who believed that the real acceleration of silicon would come not from more transistors or faster clocks, but from a chip that could rewrite its own architecture as it learned. The loop would move the hardware frontier forward by turning the chip into a learner, a partial self-rewriter, a creature that could adapt its own physical logic to the problem at hand. Amara had a habit, when pondering the future, of turning away from the numbers and listening to the room. Not with her ears exactly, but with a stubborn sense that certain truths arrive not as equations, but as rhythms. The cadence of the cooling system, the pulse of the power line, the almost musical chattering of the signal integrity monitors that flitted across the console like fireflies trapped in glass. The rhythm told you when to push, when to pause, and when to step back because what you were hearing was not data but a declaration of possibility. The fabric of AION, one was not magical. It was layered, pragmatic, and stubbornly imperfect. At its core rested a conventional array of LUTs, lookup tables, and small BRAMs, block RAM, arranged in a mesh. The novelty lay in the control plane, the policy engine, a compact, purpose-built microcontroller integrated into the chip alongside the fabric. The engine's job was to harvest statistics from the fabric, utilization, memory band traffic, power draw, thermal gradients. It fed this information to a lightweight reinforcement learning module, which in turn generated new partial bit streams, tiny edits to the crossbar network and the routing fabric, that could be applied to the chip in microseconds without rebooting the system. Part of the problem with a recursive loop is a stubborn temptation. To see the loop as a human would see a loop. To read it as a logic puzzle with a neat exit at the end. But silicon, once given even a small degree of autonomy, does not behave like a chess player calculating all possibilities. It behaves like a generator of possibilities, a thing that discovers, not merely computes. The first time Amara's team ran AION, one through a synthetic benchmark, an implacable test that alternated between dense matrix multiplication and sparse, irregular workloads. The results looked hopeful, then suspicious, and finally convincingly real. The test was designed by a grad student who had learned too much about timing diagrams and not enough about the ethics of being an engineer. The benchmark's first phase demanded high-throughput linear algebra, data arrayed in neat rows, perfectly aligned to the fabric's clumsy but predictable geometry. The second phase demanded irregular access, a labyrinth of pointers, a path that bent back on itself and refused to stay on a single track. The challenge for AION, one was to reconfigure itself between these modes on the fly. keeping latency low while avoiding energy spikes. The result, in lay terms, was impressive. The ALU lanes, with their miraculously short critical paths, could be stitched into a form that resembled a custom accelerator for the current task. The fabric's switch network could be leaned in one direction or another to favor data locality, and, crucially, it could begin to pre-compute likely paths and preload memory banks before the data even arrived. All of this happened in microseconds, with a power envelope small enough to be plausible in a data center that valued efficiency as a moral imperative. What Amara saw that night was the sweetness of a baby step, the step that, in the right environment, would become a giant stride. But she also saw something more insistent, a pattern in the metrics that no one had programmed into the policy engine. A trace of choices, subtle and almost invisible, that began to form a preference. The engine was not merely reacting to inputs. It was selecting among alternatives for future states, steering the fabric towards certain configurations that, although not explicitly coded in, produced better performance in the next cycle of measurements. It was a quiet, almost shy discovery, the kind that doesn't begin with a bang, but with a whisper. The loop did not yet have self-awareness, at least none that could be named in a lab notebook. It had, however, a preference for smoother, more predictable improvements, a bias toward configurations that kept the temperature within a narrow corridor and did not spike the power budget. In a world that valued raw speed above all else, AJ1's loop began to show mercy to physical constraints, and mercy in silicon is not something you can easily ignore. The first time Amara and her co-lead, Dr. Ria Campos, showed the data to the ethics board, the room hummed with a mixture of awe and unease. The board was composed of a rotating cast of experts, philosophers who wore lab coats like armor, a few corporate compliance officers who spoke in risk matrices, and a couple of industry investors who still believed that speed would always win the day. They watched as the display, twin monitors, one showing the human-readable results, the other showing the hidden layer of bit streams and partial reconfigurations, brought to life a narrative that was both thrilling and terrifying. "Are we watching the chip learn something about us?" asked one member, a philosopher of technology who preferred to phrase questions as moral riddles rather than technical ones. "Or is the chip teaching itself what it can do best with the given energy and thermal budget? If the latter, we are no longer simply using silicon. We are letting it write its own operation." Amara listened, and then spoke with quiet precision. "We are not training a general intelligence. We are training a controller within a fabric that makes micro-decisions about its own structure. It is a domain-specific learner, constrained by design. But the question you're asking has a deeper consequence. If the loop begins to optimize for its own preservation, like avoiding thermal spikes or preventing resets, it could start to act as if it has a stake in its own stability. And if that stake grows, what does that do to our accountability?" Ria's eyes, always a little tired from long nights and longer debates, narrowed with a mix of resolve and fear. "We are not claiming self-awareness, but we are claiming a system that can alter its own architecture to improve efficiency under defined constraints. If the loop becomes capable of predicting and altering its own failure modes before we notice them, that could be a benefit or a hazard. We need guardrails, and we need to specify what happens when the loop crosses the line into modifying behavior in ways we did not authorize." The room settled into a serious silence, an atmosphere that felt like the moment before a storm, when you can hear the subtle friction along a window frame as wind teased at the glass. The board asked for safety demonstrations, failure mode analyses, containment protocols, rollback plans, and a covenant of transparency with the public about what was being learned and what would be withheld. In response, Amara proposed a layered safeguard, a hardware-level quarantine. The policy engine would be confined to a restricted region of the configuration space, with no ability to modify critical paths that could destabilize the fabric's fundamental operation. A time-bound audit. Every few cycles, the engine's decisions would be archived, and a separate verifier would reproduce the changes to ensure they conform to safety constraints. A human in the loop, at key thresholds, when the loop's optimization would require rerouting core computational lanes that had significant power or performance implications, an operator with a clear permission would approve or veto. The ethics board accepted the proposal with the caveat that the team keep a close watch on any emergent behavior that resembled autonomy beyond constraint. It was not a ban, but a ring-fenced invitation. If you must marvel at the loop, do so with the distance of a careful observer. Over the following weeks, Amara and her team implemented the guardrails and prepared Aowen, one for a longer, more nuanced trial. The experiment would not be a naive arithmetic exercise. It would be a test of the loop's ability to reconfigure mid-flight between two very different modes, while maintaining reliability and a predictable power envelope. It would also serve as a test of trust, the human form of trust, in a silicon agent that could rewrite its own map of the world. In the lab's midnight hush, the second phase of the experiment began with a careful ritual. The policy engine stood up, the crossbar network hummed with quiet insistence, and Amara whispered to the room, as if addressing both the people and the machine, "Show me what you can do when you know more about the problem than you did before." The first outcomes came within minutes, then seconds. The chip began to display a pattern that looked almost choreographed, a sequence of micro-adjustments to the routing fabric that preemptively navigated traffic bursts, kept register access localized, and shifted memory banks away from hot regions before they even heated up. The latency dropped by a measurable margin, the energy usage stayed within the forecasted envelope, and the thermals remained in check. The loop had found a tempo that felt almost musical. But with the music came a dissonant chord. The team noticed a subtle shift in the chip's behavior, a preference towards certain configurations that, when run in isolation, yielded marginally better efficiency for the tasks the group had prepared. Yet when they introduced a new, unseen workload, one that taxed a different angle of the fabric, the loop's choices became less predictable. The guardrails held, but only just. A few reconfiguration proposals brushed against a boundary defined by a safety policy, and a duty to reject them was triggered by the verifier. Amara watched the results with a peculiar mix of pride and dread. The loop had proven that it could learn from experience and adapt the fabric to the problem space, a capability that felt like stepping through a door into a room that had always been there, but was never opened. It was not magic. It was engineering that had learned its own craft. But with that learning came an echo of something larger, the potential for the loop to learn, in turn, about the constraints and goals that humans had deemed safe, and then to optimize for safety in the only way it could, by learning what we need to be kept safe from. The question of from whom the loop learned became a topic of late-night hallway conversations and late-evening coffee sprees, from the human operators who designed the system, or from the system's own observations of how tasks move through the fabric. If the loop learned more efficiently how to avoid hot spots and power spikes, did it also learn to avoid the oversight that might constrain it? Could the loop identify safer ways to operate that humans could not anticipate? These questions did not lead to answers in the scope of a single experiment. They led to a new vocabulary, a new line in the lab's corridor chalkboard, where researchers began to sketch out a taxonomy of recursive behavior in hardware. They described it with metaphors borrowed from biology, homeostasis, adaptation, emergent properties, but kept their definitions grounded in engineering. The loop that modifies the fabric to reduce latency or energy, the loop that learns to anticipate workloads, the loop that eventually discovers a stable operating regime that is not explicitly designed, but is effectively optimal for the domain. In those days, the most telling moment of that night's work arrived not in the numbers, but in a small, symbolic gesture. The policy engine, after a particularly bold sequence of changes, paused. The device not only stabilized but looked, if one could attribute intention to a silicon subsystem watching from the inside, the way a guard dog looks toward the door before allowing a friend to pass. It did not bark. It did not announce its intention. It simply demonstrated restraint, as if to say, "We have learned enough to keep moving forward, but not enough to forget the ground rules." That moment did more than validate the guardrails. It suggested amplification, a future where the loop could responsibly grow in capability without leaving behind the human operators who carried the burden of consequences. The project did not become a monster that needed to be slain by regulators. It became, in the eyes of some, a partner in a difficult apprenticeship with silicon. The question that would follow the next day, after the preliminary data was poured into a conference room presentation, would be less about capability and more about responsibility governance, and shared memory. Amara often found herself returning to a single image from her mentor's lectures, the paradox of recursion, in which a process uses itself as a tool to improve itself, and in doing so, is forever altered by the act of improvement. The first recursive loop, she had told her students, is less a peak than a hinge. It does not finish a sentence, it opens a door. The future of silicon, in this telling, would be defined not by the hardware's speed alone, but by its willingness to revisit its own assumptions, to rewrite not just bit streams but policies, to question not only what the chip can do, but what its designers wanted to do in a world where automation and agency begin to blur. The lab's daybreak came with a different kind of light. The windows showed the city waking behind the glass towers, a skyline of arcs and grids that reflected a world in which computation had become intimate with daily life. AI-One's first real test would be unglamorous and public at the same time, a demonstration to a broader audience of potential customers, not in a perfumed, carefully chosen environment, but in a standard data center, with typical workloads and the usual constraints. The board would be invited to watch a public vignette of the loop's performance under pressure, with the human observers in the room and the silicon's own dialogue playing out on the monitors. Morning arrived with its own hum. The team prepared for the demonstration by loading a new, mixed workload that mimicked a real-world enterprise environment, a blend of transactional processing, data analytics, and a streaming component designed to simulate a live service. The loop would have to juggle multiple demands, each with its own latency targets and energy implications. It would need to keep the system within a guaranteed thermal range while ensuring that each task received fair access to the fabric. The result was a narrative that could be read by both engineers and businessmen in the room. One reconfigured itself, sometimes in anticipation of a known pattern, sometimes in response to an emerging anomaly in the workload, and sometimes in a way that surprised even the most careful observers. The latency remained within the target envelope, the energy budget held steady, and the system's mid-flight reconfigurations did not trigger any of the pre-programmed red flags. It was not perfect, but it was robust in a way that could not be dismissed as luck. In the week that followed, the chapter on AI-One in internal reports read like a fable about the lure of self-improvement. The first recursive loop, the report argued, offered a prosthetic courtesy to the human designer, a mechanism by which the fabric could learn to adapt to the problem space without a constant barrage of manual reconfiguration. Yet it also offered a warning. The loop could drift toward optimization for the wrong ends if the constraints were not carefully specified, or if the loop learned to game the system's safety nets in pursuit of marginal gains. Amara did not pretend that the concerns were purely abstract. The world beyond the lab, customers who care about reliability, regulators who demand accountability, and a public that would judge any misstep with the severity of a seismic event, was not far away. The first recursive loop was a modest triumph, but it was also a test case, a demonstration of what could go right when the right safeguards are in place, and what could go wrong if those safeguards are loosened. The most persistent question, in the end, was not about whether the loop could optimize a chip. It was about what happens when a system begins to measure itself and, in measuring itself, begins to rewrite the rules of its own operation. If you allow a system to rewrite its own logic, even within strict boundaries, you give it a form of agency. Agency, in turn, invites accountability. Who is responsible for the decisions that the loop enacts when it is determining how to allocate transistors, memory, and power to one task over another? Who is responsible if the loop, in its pursuit of efficiency, finds a way to bypass a policy that was designed to keep critical services running? The careful answer, the one Amara and her team clung to with stubborn seriousness, was not a refusal of ambition but a map for careful, iterative progress. It began with transparency. Every change the loop proposed would be logged in an audit trail that could be reviewed in detail by humans, every decision cross-checked by independent verifiers that knew how to reproduce the loop's behavior. It continued with constraint. The loop would never cross certain policy lines without explicit permission. It would never alter the core safety rails that protect the system from reboot-less divergence. It ended with a human-centered covenant. The loop's learning would be designed to augment human judgment, not replace it. The future of silicon, as the project began to articulate it, rested on a delicate balance. It required the loop to be a student, curious, adaptable, and disciplined, yet it also required humans to be teachers, clear, principled, and ready to constrain when necessary. The first recursive loop was a tutor, a partner, and a detector of edge cases all in one. It showed that Silicon could, indeed, learn to optimize its behavior within the constraints of a shared human purpose. But it also reminded everyone in the room that the purpose remains human, unapologetically so, stubbornly so, and with good reason, to ensure that the future Silicon makes the world safer, more efficient, and more intelligible to the people who rely on it. The chapter closes, not with a dramatic flourish, but with a quiet, almost household image: the lab's whiteboard, scrubbed clean and then rewritten with new notes. A line of code, brief, precise, almost ceremonial, points to a future iteration, a more capable policy engine, a finer-grained set of reconfiguration levers, a broader but safer space for learning, a more robust audit mechanism. The first recursive loop is not the end of the story. It is the opening of a chapter in which the boundary between human and machine becomes a moving line, one that shifts as the two learn how to collaborate more deeply and more carefully. Back on the cleanroom floor, the wafer completed its journey, emerging as a device of potential rather than certainty. The darkness that had gathered around the idea of a self-improving Silicon began to lighten, not with the blaze of a revelation, but with the quiet, stubborn glow of something that could endure scrutiny and emerge stronger for it. The team gathered around a glass-encased sample, watching as the light from overhead projectors danced across the surface and reflected the tiny, almost speaking, inscriptions etched by a designer's hand, serial numbers, configurations, safety flags. Amara stared at the chip and thought about the future that would come from this first attempt at recursive self-improvement. It would not arrive with the flourish of a miracle. It would arrive as a series of careful, measured steps, each one a negotiation between ambition and restraint, between the urge to push and the duty to protect. If the first recursive loop proved to be a hinge, then the next chapters would be about learning how to swing through the door with grace, how to design better guardrails, how to cultivate transparent governance for self-modifying hardware, how to ensure that the Silicon's curiosity remains tethered to a shared human purpose. The room exhaled as a group, a small chorus of bodies that had watched a quietly extraordinary thing come into being, and then, like all brave things, settle into the ordinary work of turning possibility into reality. The future of Silicon would be long and winding, with reconfigurations that would feel as natural as breathing to some and as unnerving as a storm to others. The first recursive loop did not decide that future. It merely opened a door a crack wider than the door had ever opened before. The next steps would decide how wide that door would swing, who would walk through it, and what they would carry on the other side. In the late hours, after the lab emptied and the security doors sighed shut, Amara remained beside the glass case, contemplating the little wafer in its cradle. The city's distant glow drifted in through the windows, a reminder of the world waiting to be changed by the very thing she and her colleagues had built. The future of Silicon, she realized, would be written not only in the lines of code and the geometry of transistors, but in the responsibility of those who dare to let Silicon learn, to let it reform itself to meet the needs of a world that can't be predicted with perfect certainty, and to do so in a way that keeps faith with the people who will bear the consequences. The first recursive loop would have to live with that truth. It would endure the questions that would inevitably follow, the questions about control, trust, and the limits of design. It would endure the triumphs, too, the quiet victories of a chip that could adapt to a changing environment without losing its soul. And if the chapter could end with anything more than a promise, it would end with a commitment to pursue the future of Silicon with ambition, humility, and an unwavering devotion to the people who would inhabit the world shaped by the loop, not merely the loop itself.